Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're doing question 9 from the Matric Physical Science paper 2080. It's a horrible little question. I think by mistake, many physics teachers are also maths teachers, and I think by mistake they forgot this is a physics paper and they stuck in a maths question. But thankfully, if you look at the bottom, it's only worth 6 marks. So what do we care? Let's have a look at these few miserable little marks and this miserable little question for the 6 marks. Learners perform an experiment to determine the EMF epsilon and the internal resistance little r of a battery using the circuit below. There's an ammeter, switch, a variable resistor, and there you see your typical cell with the internal resistance and an EMF. The learners use their recorded reading of the current and resistance together with the equation. There's an equation. That equation, by the way, is not in your data sheet. So they've given you an equation to obtain the graph below. And there is a graph. Graph of resistance versus 1 upon current. Now notice that 1 upon current. Why 1 upon current? Well, if you've seen enough of these problems, I just want to show you Ohm's law. Okay, there's Ohm's law. Resistance equals volts upon amps. What do you see about the relationship between resistance and amps? The relationship is an inverse relationship. And when you draw an inverse relationship graph, it is going to be a hyperbola. So to make it a straight line graph, they invert the inverse relationship, and then you get a straight line graph such as we see below. So if you take that to the top, that is now the relationship between resistance and 1 upon I. If you're taking I to the top, which is an inverse, is now a straight line graph. So they've now turned this into a straight line graph because it's the inverse of an inverse relationship is a directly proportional relationship, and there's a directly proportional graph. Just to tell you so that you've seen it before. Which variable has to be kept constant in the experiment? And the variable you've got to keep constant is the temperature of your variable resistor, because normally when the resistance starts getting low, the current gets high, and when the current gets high, the resistor gets hot, and when the resistor gets hot, its resistance increases. So to perform this experiment accurately, we've got to keep this resistor at a constant temperature. So that's the answer. Then they say, write down the value of the internal resistance of the cell. Now, if you now are able to see from Ohm's law, the relationship between resistance and current is inverse. But the relationship between resistance and 1 upon current is directly proportional. So that's why we get the straight line graph. But you still got to remember that if this is 1 upon current, as 1 upon current gets smaller, current is getting bigger. So this is the current when it's smallest, this is current when it's biggest. Current's getting bigger, bigger, bigger as the resistance gets smaller, smaller, smaller. We know that. When the resistance decreases, the current gets bigger. But the current doesn't stop getting bigger. It keeps on getting bigger beyond when the external resistance is naught. So when is the current maximum? When there's zero, absolutely zero resistance. So that's the external resistance up to there. Naught, all of those are external resistances which they added, and there you can read their values. So this must have been the internal resistance, which is -3. But resistance is always a positive resistance, so don't say -3 ohms, say 3 ohms is the, and so you just read it from the graph. But you need that value to calculate the EMF of the battery. So if you get this wrong, the 2 wrong, if you haven't, for example, gone over past papers like we're showing you how to get it, then you won't get the second part. Now, how do you calculate the EMF of the battery? You go to the formula they've given you. You've got to calculate that value. You've worked it, that is 3, actually 3, positive 3. And so, okay, so we're going to use any plot on this graph, and we are going to use this formula, and we're going to plug in the values here on the graph. So let's choose, for example, this 1.5 as our 1 upon I value, and let's go along what's between halfway between 5 and 10, 7.5. So let's use that plot and that formula. So 1 upon I is 1.5. and resistance is 7.5. Let's go and see how the memo does it. So you see here they say the internal resistance was 3. Then let's use this method here. We choose our formula. We plug in the external resistance is 7.5. There's our internal resistance. Notice it's minus positive 3. And then our 1.5, we invert it, put it on the top so that it's the inverse of the inverse. And so that I is not 1 upon I. So if we want to get I, 1 upon I, we've got to invert it. So there you see we've inverted the 1.5. You look for the R value, you look for the I value, you plug in your I value, but they don't give you directly an I value, they give you a 1 upon I value. So you're going to have to invert it, put it on top, times E, and then you solve and you get 7 volts.